Hi everyone. This is the second video of organic chemistry. And in this one, we're going to start to look at some properties of the first group, alkanes, alkenes, and haloalkanes. There are two main groups of properties. The first one will look at our physical properties, and the second one include chemical properties, which are like chemical reactions where things change. Now, physical properties, this is an important idea, and it is all about things when they change, but it's still the same substance. So a really good example is dissolving in water. So all of these are good examples. When something dissolves in water, if you think of sodium chloride, if it dissolves in water, it's still sodium chloride. It hasn't actually changed into a different substance. And so things like that are all grouped in this family, like physical properties is what we call them. So how about alkanes, alkenes, and haloalkanes? Luckily, all alkanes and alkenes and haloalkanes, all three of them, their physical properties are basically the same. Okay, they're very, very similar. So we can just learn one rule and we can apply it to all three of them. So you might already be thinking, well, alkanes, they're non-polar. And we learned that non-polar things do not dissolve in water. Alkenes are basically non-polar as well, so they do not dissolve in water. The slightly confusing one are haloalkanes. Now, haloalkanes are polar, especially, well, some of them are. I guess some of them are not. But something like fluoromethane, we learned in Unit 3 that fluoromethane is polar. But it's not polar enough to dissolve very much in water. So, and we'll see later that hydrogen bonding is the other thing that is very important when understanding when things do dissolve very well in water. And so haloalkanes, yes, they're a little bit polar, but they're not very polar. And so they dissolve a little bit, but even when something dissolves a little bit, we usually call it non-polar, or sorry, insoluble, because it doesn't dissolve very much. All right, how about boiling point and melting point? Well, you may have heard of methane and ethane and propane and butane, and you may know that those are all gases. That means their boiling point is very low. They're already gases at room temperature, at normal standard temperature. And that's true for all of the alkanes, alkenes, and haloalkanes. And that's because they're non-polar, so they have only dispersion forces. So again, there's this link with Unit 3, where we learned about dispersion forces and dipole-dipole. And so, and haloalkanes, if they're polar, they might have dipole-dipole, but dipole-dipole's not very strong. And none of them would have hydrogen bonding with just these three groups on there. So they have very low melting points and boiling points. But as size increases, dispersion forces increase, and so the melting point and boiling point will increase as well. We haven't talked much about density. Density is how heavy something is for the same size. And so a good thing to compare things to is water. And if you think of oils like petrol that we put into a car, it's mostly octane and it floats on the top of the water, or cooking oils that we use in cooking. And those are quite large molecules, but they are less dense than water. And again, this is partly because they don't hydrogen bond, so the molecules are not held tightly together. Okay. And so as a general rule, all alkanes, alkenes, and haloalkanes, usually they would be less dense than water and they would float on top of the water. And now for conductivity, and it's mostly just so you've heard of this property that I include this one, is about conducting electricity. Now, alkanes and alkenes and haloalkanes, they do not have ions, they do not have charged particles, and so they cannot conduct electricity. And they don't dissolve ionic substances either. So water can conduct electricity mostly because it will dissolve a salt. Then it will conduct really well, like the salt bridge that we learned in the electrochemistry unit. But haloalkanes cannot do that. All right, so what about the chemical properties or the reactions of these three? In this video, I'm only going to talk about alkanes and alkenes chemical properties, and we'll talk about haloalkanes in the next video, just to give it a little bit of space. So I've organized it here by type of reaction. So combustion reaction is one that you already know. We know that from the energy unit. And alkanes and alkenes, we saw lots of those in the energy unit when we were talking about combustion. They undergo combustion very well. Haloalkanes, not really. Some do, but some don't. So let's not worry about haloalkanes for combustion because it's a bit confusing. Another type of reaction is called a substitution reaction. So, and we'll see several examples of these many times throughout the year, throughout this unit, substitution reaction, but this is the first time we see it, and alkanes can do substitution reaction with two main reagents. The first one is actually the major one, chlorine gas, or I guess dissolved in something, but chlorine Cl2. And so substitution is just like it sounds. Something is lost and something else comes in and replaces it, substitutes it for something else. So let's look at a nice example. All right, so I'm going to use methane for this example. And in this substitution of alkanes, it's only the hydrogen that can be replaced. So when chlorine reacts with hydrogen, one of the hydrogens is replaced with one chlorine. And HCl is produced as well. You can write that if you want, but many times you'll notice people do not write this. The other thing you'll notice is the way I'm writing this reaction. I've written Cl2 above that arrow. And this is quite a nice thing in organic chemistry. You do not need to balance the equations here. We're interested in the carbon group. What does it change into? You do not have to balance it. You don't have to worry about that other chlorine, what happens to it. But it does make HCl. Now, this is a bit complicated for alkane because there's not only that one hydrogen, there are more hydrogens on here and they can be replaced as well. So we can get one hydrogen being replaced, or we can get two hydrogens being replaced, or three. So there is a mixture of products. All of these are possible and we get a mixture of these. I don't know how much of each one. It's not balanced. It's not 1 to 1 to 1. We could, if we had extra chlorine, then we'd get a lot more of this product here where all four of the hydrogens are replaced. If we had less chlorine, then we'd get more of this, but we'd probably get all of them no matter what. And so that's a first look at substitution reactions, one of the major ones that we learn that alkanes can do. And just as an aside, there is another reagent that can substitute an alkane, but it's not very easy. But bromine, Br2, can, but it does need UV light. UV stands for ultraviolet, and so it's a high energy type of light, and that will help the reaction happen. So haloalkanes can do this type of reaction as well, but we'll come back and talk about that, see that some examples of that later. Now, alkenes only do one type of reaction other than combustion. We saw combustion up here. Alkenes can burn. But other than that, they only have one other type of reaction. So this is a very important type of reaction to know about, called addition reaction. They have a double bond. Now, if that double bond changes to a single bond, all of a sudden there are two new places for something to fit. And that is the idea of the addition reaction. So let's look at some examples. So from a double bond, it changes to a single bond. So there are two new places. And if it was Br2 that we were using as the reagent, then that would get Br and Br on the two sides. So this time there's not anything else that's produced. The Br2 becomes Br, Br is both bonded to the two carbons where that double bond was. And so there are 6 main reagents that I'd like you to be familiar with this year. They're the ones I'm going to use: Br2, Cl2, H2. Also with H2, you need to know it needs extra help. It needs a catalyst, platinum metal, and it needs to be quite hot, about 200 degrees Celsius. Okay, so pretty hot. And then there's another group. There are these ones down here: HBr, HCl, H2O. H2O also needs help. It needs a catalyst. Sulfuric acid is the catalyst for that one. Now, why have I put these ones on the second line? I've done that on purpose because here it's two different things. It's H and Br on the two sides. And so if it's not ethene, if it's something else with more than just two carbons, then they might not be added in the same way. So let's look at that. So far here, I've just set it up and I've changed that double bond to a single bond. You don't have to draw the single bond there, but I'm just trying to make it really clear. And the HBr is added to those two carbons because now they have an extra space. So they could be added HBr, or they could be added Br on this carbon and H, the hydrogen, on that carbon. So you might think, well, okay, that's fine. So there are two different products. One is 2-bromopropane, one is 1-bromopropane. They are different, they have different names. But maybe we would think, well, 50% of them will be this one and 50% that one, but that's not true because these two carbons are different. The carbon in the blue here has two hydrogens bonded to it, and so that means it's actually a bit more negative. The carbon of the green here only has one hydrogen bonded to it, so it's a bit less negative. It changes its charge a little bit. And so those two carbons are in different environments. And so the hydrogen more easily is bonded to the carbon that already has more hydrogens. And so that is what we call the major product. And by major, it's more than 90% of the product is that one. The second one is called the minor product. Okay, so it's less than 10% of the product will be that one, where the hydrogen goes to the carbon with fewer hydrogens on it. If the two carbons on the two sides have the same hydrogens, then there's no major or minor, but there often is a major and minor. And this is called Markovnikov addition, or the Markovnikov rule. Yep, I probably don't need to remember how to spell that. It's just a person's name. But if you see that, if somebody says use the Markovnikov rule to give the major and minor products, this is what they're talking about. Just the hydrogen goes to the place with more hydrogens. And I like to think of the Markovnikov rule as the hydrogens are best friends with the hydrogens. So the hydrogen will go to the spot that already has more hydrogens. They're attracted together, or they're in love. Aw, so cute. So those are the reactions I wanted to include in this video. And in the next one, we'll look at the haloalkane reactions, and then we'll have learned all of the reactions we're going to learn for this unit for this section, alkanes, alkenes, and haloalkanes. And there are some practice questions in your study guide. We can look at those together and you can ask me any questions you have. Bye-bye.